Huh. Hmm. Uh, oh, nice. Du, 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 du. Filters, audio filters, microphone. Okay, I think that's good enough. Yeah. Huh. Hello, non-existent audience. It's me, Sandeep, from Halfwire TV. If you're a robotics enthusiast, someone who likes pain or seeing others in pain, do consider joining the community. The community has recently exploded, and by exploded, I mean it's gained over 140 members across 15 different countries in such a small amount of time. And why the hell am I seeing so many dropped frames? Hmm. The internet's decent. For some reason, it's going out though. Mm, mm, maybe it's a setting thing. Stream. Uh, shit. Mm, Uh, Apparently the Internet Explorer now. My God, what's going on? Should be good enough. Hope so. Yeah. Hmm. So I'm trying to understand a research paper relating to trajectory optimization of multi-legged robots. What that means is I need to find the most optimum trajectory for a robot joint to move from position A to position B. Like the position is predefined, the speed is predefined. All I need now is the trajectory. But the constraint is it must be a single equation for every possible environment and every possible multi-legged robot. And that's hard, mainly because I am still a beginner in kinematics and dynamics, especially in the case of robotics. So far, I have covered frame transformations, and I think I have derived a few things or not. Okay, apparently, apparently, effed up a bit. Uh, Couldn't be a thing that's too hard to fix right now, but let's see. So for context, I'm trying to take out the rotational matrix when I rotate a frame about the z axis. And in order to do that, I'm looking at the frames from the z axis. So it would look something like uh, it would look something like this. A top view. I'm still unsure where I have where I got things wrong, but I hope I can do that in a few minutes. I have managed to make the same mistake twice in a row now, and two different problems, but of the same class. I mean, just take a point attached to the rotating frame, let's say point P, and then we just draw out its coordinates and both the frames. We know that the point attached to the rotating frame wouldn't have its coordinates change in the rotating frame, of course, because it's fixed. Therefore, U would remain same and Py would remain same as well. One thing that I am concerned at is I might have named them wrong. And yes, I have. I somehow have managed to interchange PO and PN. Let's fix that quickly before it becomes a mess. Mm, yeah, and with some quick trigonometry, we arrive at these results. I mean, I have to change these, of course. And then we just convert these system of equations into a matrix. And again, let me cross this out and make a fresh one because I fucked that one up. So yeah, px, py, pz, that would equate to uh, mm, some matrix, and then the moving, the rotating frame. So what this does is it gives us a magic matrix that when pre-multiplied to the rotating matrix gives us the coordinates in the reference frame. Oh, as I'm assuming the world frame. It's pretty easy to convert it actually. We know that Pn and Ppo are right here, so we need a few terms that convert this into this, and that's pretty apparent that it's cos theta and then minus sine theta and then a 0 to eliminate PA. Similarly, sine theta and then a cos theta and another 0 to eliminate this for PY, and PZ wouldn't change. So the PZ part, I mean PZ is equal to PA, so a 0 to eliminate PN, a 0 to eliminate PO, and a 1 to keep PA. I mean, yeah, that was a relatively quick fix, and it's absolutely correct. So let's move on with the book. Equation, uh, this is just a way to represent everything we did in a more concise form. And another cool thing about this is this can be chained as well. So you could have a lot more transforms, let's say, from rotating frame. This is basically from rotating frame to the universal frame, given that this point is in the rotating frame. And you could also add many intermediate ones, like the frames that change the coordinates from another frame B to the rotating frame, and then one that changes it from rotating frame to frame B, and so things just start canceling out. That's the main thing. And yes, the way to read this is from the right to the left. So the point P is in the rotating frame R, and this transformation, this magic matrix, transform the coordinates from the rotating frame R to the universal frame U, and that gives us the point P in the universal frame. I mean, the questions are pretty easy. These are just formula based, so I'm not gonna bother doing them. representations of combined transforms. I mean, if you had to combine transforms, you would just re-multiply them over and over. That's pretty straightforward as well. And I have done this question once. Again, pretty easy, just time intensive. These are a sort of things that could easily be done using solvers like MATLAB. Mm, Transformation relative to a rotating frame. Okay, transformations have a measure related to the reference frame. However, it is possible to make transformation related to the axis of moving or current frame. This means, oh, so it just means rotating a frame about its own axis. I know it feels weird, but trust me, it isn't that hard if you just open up your mind and start accepting a few things. Just accept that it can be done. Try to do it, and it will pretty much be clear. It's not something that I can or will show you, but it's pretty fun. Basically, what you do is just um, instead of pre-multiplying the matrices, you just post-multiply them. That's it. And if we had both rotation about their own axis and then translation, oh wait, rotation about z axis, yeah, then what you would have to do is both of them, like uh, the frame B was rotated about the x axis by 90 degrees. So you would pre-multiply this once, and then about the current axis you would post multiply this another time. Wait, we would translate it about the axis. Okay, fine. So we post multiply this once, and then it was rotated about the z axis. We pre-multiply this once, and then translate it about the o axis. So post multiply again. That's it. Pretty simple stuff. Inverse of transformation matrices. I haven't read too much around this part that thoroughly, so it might be an issue. Mm, okay. No, it's not related to inverse kinematics at all. It's just inversing a motion, inversing a transformation matrix. That's again pretty easy. I mean, what you do is just simply find the inverse of this matrix by calculating 1 by a, like 1 by the determinant, and then adjoint of the matrix. And adjoint can be calculated by taking out the transpose of the matrix. Like a transpose is literally just, I could show you the transpose in my notes. Uh, Ah, shit. Position analysis. Yeah, just take the rows and then flip them to convert them into columns. That's it. Then after transposing the matrix, you replay like you just uh, cover these elements. For example, let's say we are finding out the minor for this element, then we would cover the elements in its axis and then cross multiply them. So this with this minus this with this. That's it. Repeat the same for every element, and you should have the adjoint of the matrix. Yeah, the inverse matrix of the rotation matrix could be found using the same method, and coincidentally it's the same as its transpose. So cool. This takes off the load, I guess. Just take a regular rotation matrix and then just convert the rows into columns, and there you go. You have it. Can say the same about translation matrices though. Actually, initially I planned this stream to be like a Discord call, but then I don't know, I just changed my mind to just quickly go through everything, mostly because I was running out of time. Wasted a lot of time today. Yeah, I'm just gonna speed run through this and maybe let the other people discover it slowly at their own pace. For the translation matrices, location regarding the matrix and proportion rotation matrices, approximately simple transpose and discriminatory. Position matrices of the imaginary matrices, negative of the dot product of the p vector with each other and OA. Oh, ow. Okay, yes. So what that's saying is we have our uh, translation matrices as so. Then the position vector of the translation. But in case we wanna invert this, we would literally just find out the dot product with the NOA vectors. I think I think that's what it says, right? So remove these and write minus p dot n minus p dot o minus p dot a, and that should be enough. The preceding result is only true for first you get the same result with the second method mentioned in the appendix. A matrix is not a unitary matrix, not all rotation matrices are unitary. Okay, only rotation matrices are unitary. The preceding result is only true for simple 3 by 3 rotation matrix is the representation of a location for a 4 by 4 transformation matrices when we divide it by the two portions. The rotation portion of the matrix can be simply transposed that it's still unitary. The position portion of homogeneous matrix is the negative of the dot product of the p vector with the blah blah blah. Cool. As shown, the rotation portion of the matrix is simply transposed. The position portion is replaced by the negative of the dot products. Uh, can I set up keybinds for the scene changes? Switch to scene. Uh, I guess the co-pilot button, super shift, whatever. So what does this do? Eh, oh, cool. So maybe hotkeys. This could be super. Mm, maybe uh, alt up and then alt down. That makes a lot more sense. Nice. This does not look like a conventional rotation matrix. That bugs me. I mean, I know it has a position portion as well, but I'm talking about the part which is being referred to as the rotation position. It's a combination of the rotation part and the translation part because it mixes blah blah blah. If you're talking about the top left, then beyond that doesn't look like a rotation matrix. Looks cos theta, sin theta, etc. It just looks like the moving frame. Ah, the moving frame, the moving frame. Huh? Where the moving frame's axis point. Huh? Oh, that does make sense. Oh, oh, it is the frame then. Oh, damn, damn, yeah. So I guess that's a really fun and easy way to simplify this. Basically, what they're talking about it is if we have the moving frame like so, uh, in a way, I mean, it would have been easier if I just place it along something. So what they're referring to is that what we just found out, like the fact that we found out in the equation, if cos theta, what these essentially are simply these lines, right? Oh, wait, this is about Z. So forget this for a sec. Yes, we have this equation ready, but I guess that will become a lot more overcomplicated. We could use this. Yes, this is a really good one. So basically, what this result is are simply the N, the O, and the A axis. Exactly how this is the vector A, and this does not change because this is directly along the thing we are rotating about. It's along the axis we are rotating about. So that's just constant. Then this this vector is simply uh, I guess x cos theta plus x sine theta, and this one is uh, o cos theta about the y-axis, and then minus cosine theta. Oh, damn, this is pretty easy. Brother, that's literally so easy. That's literally so easy. It's probably the best thing I've found yet. Uh, you know what I did right now? I just got to my roommate and celebrated my little win because I did not think that this would be so easy. I don't I don't even need to remember any formulae right now. I could just derive the rotation matrix about any axis in like a few seconds. Like that's literally what it is. You just make a matrix and then you write the corresponding N, O, and A vectors, and then you just find out the components about the reference frame. So uh, this vector becomes uh, this unit vector becomes, because it's a direction vector, so let's just take a unit vector. So 1 cos theta about the x-axis, cos theta about the x-axis, and then and then uh, sine theta about the y-axis, and then for the O vector, the cos theta about the y-axis, and then minus sine theta about the x-axis, and then the A vector stays the same, and then we shouldn't care about the last two. Why do we not care about the last two? Hmm. Oh, it's because they do not have any components along the z direction. Nice. And the logic is we just uh like multiply the frames uh like the directional vector frame to the actual frame, and then puts it just puts the frame into that orientation. That does make sense. That does make sense. That does make sense. I mean, if it doesn't make sense to you right now, I would recommend seeing that in Euler's form. Because if you convert that into Euler's form, it would be e to the power minus theta or iota theta. It would be e to the power minus iota theta. And if you multiply that with another e to the power iota function, the thetas would just add. So we are just changing them. Oh my god. Oh shit. That's so easy. That's so easy. Nice. I could derive this in a sec. I don't even need to remember this. This is all bullshit. This is all bullshit. The formulas are bullshit. I don't need any formulas. Calculate the inverse of the transformation matrix. Just transpose this and then take the positional vector, find the dot product with the x-axis, and then add a minus sign, negative sign. So this and the dot product with the n-axis. So this thing with dot product with this. Yeah, yeah. That's pretty easy. Let's be honest, that's pretty easy. In a robotic setup, a camera is attached to the fifth link of a 6 to F robot. It observes an object and determines its frame relative to the camera's frame. I really wanted to make notes for this as well for my future reference, but I don't know. It's gonna take a significant amount of my time. So let's just carry on for now. I might make some notes, especially for explaining how I derive the rotation matrix and what these. I mean, these are pretty self-explanatory. Come on, I don't need another set of notes just for that. The only thing that might be necessary is my new derivation for the rotation matrix. In a robotic setup, a camera that has a fifth link object to a robot that observes an object and determines its frame relative to the camera's frame using the following information to determine the necessary motion of the indicator must go to get to the object. Link, okay. The cam to fifth. Mm, at the end, we just need the transformation from uh, the ground frame, right? H is the end effector, I assume, and this is the object. How do we even need at the end? What's E? E. End effector. What's H? Do I care what E is? Hmm, This. Let's do it, I guess. What's E? E is the end effector frame. And what's H? H is the hand or reference frame of some fixed calibration frame. Define relative to length. Five. Uh, the necessary motion the end effector must make to get to the object. That would be the end effector to the object. That's exactly what we need. And H is some intermediate frame that we do not care about as of now. Yeah, we just find the things that are related like this. These can cancel out, and then these can cancel out. So we just put these two together and then these two together because once they do cancel out, what's left is no, wait, no. If we do cancel these out, we have 5 till object and then link 5 till R, link 4 till R. Wait, let's not take that approach. What we need at the end is the end effector to the object. So let's start with the end effector to the object. And then let's try to form an equation. So, till link 5 till reference. Ooh, ooh. Oh, yeah. We just take up the equation from the object till the reference. Do the same for this side. Oh, the way we know that, the way we get the idea for doing that is we know that we want the object till the end effector, and then the only thing that could equate that is another transformation matrix containing the object's reference. Yeah. And once we find this, pre-multiplying this transformation to the frame of the hand, the end effector would give us the position play. Mm, what I have is this shit. And why is this important? The question did say to determine the necessary motion the end effector must make to get to the object. So let's say we have the frame of the end effector, and then the frame of the end effector. So what's the relation between these two? Something does not make sense. Hmm. What will the object frame do end effector frame transformation that we obtained here? Let me. The orientation of the object expressed in the end effector's own coordinate frame. Hmm. Oh, ah, ah. That's because this part at the top left is essentially the orientation of end effect, the what is it? Is the end effector? No, it's the object's orientation related to the end effector, right? Yeah, the object expressed in the end effector's own coordinate frame. The object's orientation relative to the end effector and the position of the object relative to the end effector. Oh, so now I can generate the oh, so I can just translate and rotate the end effector along its own axes. And the way I would do that is, mm, okay. So basically, this is the orientation of the object with respect to the end effector. This is the position of the object with respect to the end effector. Now we can translate along these. No, we can like inverse the rotation by just transposing this. Right? I hope so. And then we could translate along these, perhaps. It tells you the motion command to give the end effector so it moves from where it is now to go inside a reach with the object. Reach the object. The position part tells you the translation the end effector needs to make. Rotation part. Oh. Well, the translation makes sense. I would just translate along the end effector's own frame with px, py, pz amounts in the end effector's three axes, right? Mm-hmm. Just move the end effectors. Translation gets the origin to coincide with the if you want to identify them as the youngsters, you need to rotation part 2 and the order matters. So you rotate first and translate along, you would actually overshoot because the translation will be in the original interface frame. Clean way is moves the origin is valid as long as they are rotated. If you need, would typically apply the homogeneous transform as a single rigid motion. How would I rotate in insane angles? So one of the objects axes points expressed in vector's current coordinates. So if rotating to align with the object physically means reorient the interceptor so it's on XYZ axis, swing around to point in exactly the object's X direction. Yeah. Oh, oh, make the frame vectors that way, and the actual path is the motion planners. I gotta note this down. I gotta note this down somehow. Rotation matrices. These are simply this find components of mm, will get mm, will get X vector as n, obviously. How do I just need something taller. Obviously, and then only x form, and then this would be, and then this would be O vector can be expressed as y cos theta j cap plus no minus y sin theta I cap, then the a vector can be a a cos theta j cap plus a sin theta I cap. And then the matrix would be I would place the n here, the O here, the A here, the x components here, the y components here, the z components here. So what I need to be able to do is transform points as well, right? I need to transform vectors. So if there's a vector in the reference frame, if there's a vector in if there's a vector in the moving frame, then this should be transformed to the reference frame or the universal frame in this case. So essentially, basically, this is an x, this is an y, this is an z, this is an n, this is an o, this is an a, n, o, a. Take this to this. And the best way to do that would be simply to it. I guess the x-axis is the n vector, the x, oh fuck, the x-axis would literally stay the same as the n. That would mean I can get away with doing shit like this. So now when I multiply this with this, I get the x position. When pre-multiply with this would get me the x position as just Pn. Similarly, the y position can be accessed by, first of all, ignoring the n, then having a cos theta here so that it becomes this point multiplied by cos theta, right? And I think that's what I did. I'm mixing two concepts and overcomplicating shit right now. Instead of doing all this bullshit, let me just consider the N, O, and A axes as three unit vectors and just write them as components of X, Y, Z. I guess that makes sense too. If I continue with that, then it would be uh, the N vector would just be 1, 0, 0 because it's along the x-axis. The O vector would be uh, no components along the x-axis, and then a cos theta component along the y-axis, and then a sine theta component along the z-axis, and then A could be written as a cos component along the z-axis, and then a minus sine component along the y-axis. Yeah, that does make more sense. But again, this probably is a really good derivation, but currently it's just for quick derivation slash memory, not for a full-fledged one, just because I'm not sure if I'm exactly right. Hmm. So, what time is it in stream time? It's 1:15, so I might have started at 1:13. I would suppose so. Uh, yeah. So, watch stream hash to 1:13 when I wrote this. Although exact realization was earlier. That's why I need to stream more often. I have so many realizations that I would just forget. Damn, someone did watch me for like 7.5 minutes. Luckily, someone from the community. That's cool. Hmm. Now I'll just copy what rotation matrices are. What rotation matrices essentially are. This full on NOA frame written in a homogeneous manner. This unit directional surface. And how does that work? Imagine multiplying in Euler's form with theta. The theta changes when multiplied. Because they are unit vectors, they can always be expressed in terms of cos theta slash sin theta, like the original one. And the columns are the moving frame, and the moving frame is the rotation matrix. Who is the viewer? Am I the viewer? Am I doing my own stream right now? That's counting as one. I have no idea. Could be me. Could be me. Ah, ah. Let's see. Okay, someone is watching. I'm not sure who. I'm not sure if someone was watching. There is it myself. Could be myself. Um, no. Kiss. No, it's just me. And it's not myself. Could be someone else. Need, perhaps. Hmm. I'm not sure. Am I audible? Yes, I am audible. Who the hell has been watching for like 17 minutes for now? Damn. Thank you for your time. Thank you for your patience. Hmm. Full transform would be rotation, position, forward and inverse kinematics. I think that is everything I just decoded. Oh no, wait, I forgot a very important part. How to use transforms practically. Hmm. Let's say we get transform from the object to the end effector. So we get the pose and orientation from object frame with respect to end effector frame. Now we can move the end effector to, i.e., the relative pose and orientation to that suppose relatively and that orientation about its own axis. So no weird conversion. How handled by motion planners. Forward and inverse kinematics. Suppose we have blah blah blah. Suppose we have the robot whose configuration is known. This means that all link lengths and joint angles of the robot are known. Calculating the position and orientation of the robot is called forward kinematic analysis. Blah blah blah. Yeah. This means that robot is rotation. Oh, instead of substituting the known robot variables in the robot kinematics equation, we need to find inverse of the equation, and we'll also find the necessary values to place the robot at desired location or rotation. In reality, inverse kinematics are more important since the robot controller calculates their own values something of these equations and blah blah blah. You can order to the configuration of robots, establish the rotation, then we calculate the position of rotation. This equation then we use to derive the inverse kinematic equations. You may recall from chapter 1 that in order to position or orient a rigid body in space with attach a frame. Yeah. I mean, we already know this one. Sun with the position and origin of the frame of its orientation. We actually want to conclude what transformation matrices actually are. Am I in the cam mode? Yes, I am in the cam mode. So, trust me, this looks way higher quality in OBS than it does on YouTube. Fuck. What transformation matrices essentially are? If you know transformation matrix from object and effector, you could move the end effector. Okay, this gives you the object's position in the end effector's current frame. You simply need to move the end effector along this frame along this frame. Along this frame, and uh, this frame, both position and orientation wise, I, i.e. move the position, the origin of end vector frame from 0, 0, 0 to px, py, pz in its own frame, and orient its coordinate axis to be this. These. Damn, that's heavy. Okay, अभी तक अभी तक अभी तक हाँ damn so क्यों नहीं गिरा जैसे वहाँ जैन सर पावर सप्लाई का पीपीसी बना देते तो इसमें भी एक पूरा चैप्टर दे रखा है रेगुलेटरी डीसी पावर सप्लाई के लिए Cartesian coordinates will be three linear movements and this type of robot actuators and positioning and blah blah blah. Only the position matrix is required. Yeah, cylindrical. No. Rotation of alpha about the z-axis, then a translation of L along the z-axis. I would rather use this than ever use this. This is hard to remember. So essentially, Cartesian transformation is I mean, we don't have to follow this framework, but it might be a good idea to do this in certain kinds of robots, certain kinds of manipulators, actually. If we go for a general robot, then these may not apply. It's basically translation of R and then rotation and then a translation again along the z-axis. Translation over the z-axis can be expressed as the z-axis would stay the same, and then for the x and y, it's and the cos theta term out the x-axis and sine theta term about the y-axis, and then uh, oh yeah yeah so sine theta no a cos theta term out the y-axis and a minus no wait I mean I could find this out if use a paper and a pen, but I'm just too lazy to do that right now. Suppose you desire to place a robot and as blah blah blah, calculated joint variables. Hmm. Restore the original orientation of frame frame over the angle minus alpha different portion between the result. The frame will be the same location but will parallel the reference frame again. Why? How does I just had to place the cylindrical robot at this position, then can't I just translate it? Suppose you desire to place the origin of the hand from the cylindrical robot at this calculation variables of the robot, setting the components of the location of the frame of the origin of the frame from the cylindrical matrix. We get this and this and this. Therefore, L as uh, uh, 7. No, so we just compare these equations and then get the angles. Joint variables of the robot. Yeah. लोकल लोकल सर्वर पे लगे कहाँ है अच्छा ज्यादा लोकल सर्वर तो पता नहीं हो गया होगा मैं भी सेक्शन में आता हूँ वो ना हो ही नहीं सकता